Hello and welcome back to the Sounds of Vegas. If we watch this little program, you can ask a couple different questions. What is it and what are the objects there? On first blush you see three objects. What is apparently a gray square, a pulsating green circle, and some light which is off the screen illuminating both. This is a visual Python program, and I've arranged it such that every 3 seconds the green object resets back to its original condition. You'll notice that the green object grows equally in all directions and that it intersects the sphere, but we really can't tell much more about it unless we look really close. And if we look really close at the green crossing the gray square, you'll see that there is in fact something else happening there, because there appears to be a little bit darker green on the leading edge and a little bit lighter on a trailing edge. Well, the whole point of this is that perspective matters, because if we rotate the perspective a little, all of a sudden we see that the square is in fact a cube and that the circle is a sphere. And what we're going to demonstrate here with this is that a muzzle gunshot, which can be modeled as a point source that propagates in a spherical pattern, looks roughly like this. Now there's no scale on this, so you can't tell whether that is a Borg ship in space and the Enterprise just exploded, or whether that's, the Blue Man, part of the Blue Man building in Vegas, and that's some gun exploding. But in gunshot acoustics, there's more than one type of propagation phenomena, and that will become the very distinct difference between a muzzle blast, which looks a lot like this green sphere, and the shock wave, which looks much different and has much different properties. I'm visual, so no matter what the numbers say, I like to see it in some three-dimensional shape that I can lay my mind around. So what can we say about this model? And it's basically a computational physics model of a real phenomena, and it has its limitations. It's approximate, meaning that it's not really what happens, because the muzzle blast that is created by the exploding gases coming out of the end of the gun is more directional than a sphere, and not exactly a sphere itself. But we can still use this model to give us a good idea of what happens when that muzzle blast reaches a point in space. The leading edge of this sphere represents what we would hear at some point from the gun, and what it might feel like, what it might look like on a scope or a spectrogram, or what gets recorded on a recorder. Interestingly enough, by changing the perspective, we can kind of make this look like anything. If we have what is essentially a perspective that has the cube on the opposite side of the sphere, it looks like, once again, a circle, but we notice that when it intersects the cube, that it's clearly not just a circle. All the points along the leading edge that are at the same distance from the radius, or same distance from the center point of the sphere, record, hear, or experience the muzzle blast at the same time. So if you got one person to the right over here at, say, 10 units, and a person over here to the left at 10 units, then even though they're 20 units apart, they still hear the muzzle blast at exactly the same time. And this becomes really important when you start asking questions of, well, what's the expected time of arrival between two observers? And that's kind of the wrong question to ask. The real question you should be asking is, what's the time of arrival at point A and point B relative to the center of the sphere? That is, sound propagates from its source to its destination. And every destination is a different path. And even though they may have the same or different times of arrival, it's still a different path. For example, on the right side over here, everything that would occur between the center of the sphere and the thing to the right, if there were cars or buildings or everything, would have some influence on that sound. Similarly, over here, behind this sphere, the sound would be different than what was recorded to the right, even if it was the same exact distance from the center of the sphere. And this can become quite confusing if you're trying to make an analysis between recordings of the muzzle wave, because you can't base your questions on a ground perspective. You must base your questions on the perspective from the center of the event source, which is one event, even though it consists of many multiple trillions, billions, godzillions of particles, to the point at which the wave is intercepted. And the leading edge of this is the part that gets intercepted, and there's a fixed amount of energy in the muzzle blast. When the round chambered explodes and the projectile moves along the barrel, and then it exits the barrel, then the gases behind that projectile are released, and that causes the muzzle blast. And at that point in time, there's a fixed amount of energy in that, and as it expands outward, that energy is distributed over the entire surface of the sphere. So at every point in time, the sphere grows bigger, and the amount of energy per unit area on the sphere decreases, and that's why the sound becomes quieter the further away from the center of the sphere that you are. From a perspective of below, if you want to call it below, it could be anything, you could, or above for that matter, you could look at this and say, well, if I've got a person over here, kind of behind and to the right of the building, when would he hear the muzzle blast? Well, it's a fairly simple calculation, even though it's in 3D space. It's what we call the Pythagorean distance between an observer here and the center of the sphere. And that's, there's an XYZ coordinates here at the center, XYZ coordinates here, and you just subtract the corresponding X from X, you square it, do the same thing for Y and Z, add them all up and take the square root, and that'll be the distance, the Pythagorean distance between where the observer is and the center of the sphere, which is the source of the sound. If you have another observer, which is, well, I don't know, say on this little edge here, you could take and do the same process, and you can calculate the time of arrival of the muzzle blast at that point. So if you ask, well, how long does it take for the muzzle blast to travel from this edge of the sphere to that observer over there? That's the wrong question, and you'll get the wrong answer. You have to ask what the time is from the source of the event to me, or the observer. You calculate that. You calculate the same thing for the other guy. You subtract the two, and you have the difference in times of arrival. Now there are special conditions where if you position yourself or two observers in a straight line relative that intercepts the center of the sphere, then it becomes a little simpler, and you can ask the question of how long it takes the wave to propagate from one observer to the next, because they're all on the exact same vector, just separated by distance. However, they won't hear the same wave, because in the time it takes from observer 1 to observer 2, the sphere will have expanded, and therefore there'll be less energy. So the one observer will hear it louder, and the other observer will hear it softer. And everything in between alters the wave. Well, how much does it alter? Well, let's stop for a moment, and let's say this was a 1 mile square cube Borg ship, and we're on the outside here. Then our ears, have a very small area. A microphone has a very small area, and when the expanding green sphere hits the microphone of the ears, it could be 1/trillionth of the area that contains the entire energy of the muzzle blast. And everything in between, including our ears and our brain or the microphone, alters the perception of that sound. So for example, recording on an iPhone versus recording on a cop cam, there's going to, even at the same exact location relative to the center of the expanding sphere, are going to produce two different waves, or they're going to record two different waves. They produce nothing. And then when you add in to that the complexities of the muzzle blast itself, which is directional to some extent, you can see that it gets pretty complicated. In fact, it's so complicated that if you fire 5 shots from the same rifle at the same position, traveling along the same exact, well, they don't travel along the same, firing along different paths. Well, actually, let's back up. 5 shots fired from the same rifle. The muzzle is fixed, therefore the bullet travels the exact same path, and everybody along the path of the bullet is going to hear approximately the same sound, lower in volume with some nuances created by whatever was between, the center of the sphere and the observer. However, if you take an observer that is off to the left or off to the right or any distance in between, then the wave that gets recorded is so different as to look like an entirely different firearm. And you have to take that into account when looking at the audio, if you're at least trying to figure out what type of weapon it was. So anyway, wrap your mind around that, and the next little segment of video will talk about the supersonic shockwave, which is an entirely different phenomenon.